Up until now, we've seen how a carbonyl, carbon, which is very electrophilic, can be attacked by oxygen nucleophiles. But a carbonyl carbon can also be attacked by other types of nucleophiles. And what we're going to see in this next reaction is the carbonyl carbon being attacked by a nitrogen nucleophile. Let's talk about nitrogens for just a second. There's a lot of nitrogen in the air. In fact, around 80% of the air that you're breathing right now is nitrogen, not oxygen. Oxygen makes up only around 19% of the air. The nitrogen in the air is really stable. It's molecular nitrogen, and it looks something like this. If you heat it up really, really hot, and I'm talking like really hot, like in an exploding volcano, or certain microbes have enzymes that can react with hydrogen. There's a tiny amount of hydrogen in the air. There's more hydrogen in processes. It gets belched out of the earth sometimes. Now this isn't going to be balanced, but you can see how the nitrogens can react and form a molecule where the bonds to the nitrogen go to hydrogens. Now keep in mind the nitrogen has that lone pair. Remember, nitrogen is in group 5a, so if you draw the Lewis dot structure, you would have the 5, and so it can form 3 bonds, and it has that lone pair at the top. So we have this molecule here, where nitrogen can combine with hydrogen. It's sort of like the nitrogen version of water. And kind of like water, it's very common on Earth. It's a molecule called ammonia. Now, if you just like if you take water and you start replacing the hydrogens with carbons, so for example, if you replace one of the hydrogens with a carbon, then you get an alcohol. So likewise, if you take ammonia and you replace the hydrogens with a carbon, you end up getting a molecule called an amine. And the word amine is recalling the fact that it comes from ammonia. Now, there are 3 different types of amines. So amines are like the nitrogen version of alcohols. There are 3 different types of amines. You could have an amine where the nitrogen is just bonded to 1 carbon, and that would be a primary amine. You could have an amine where the nitrogen is bonded to 2 carbons, and that would be a secondary amine. Or you could have an amine where the nitrogen is bonded to 3 carbons, and that would be a tertiary amine. Now, we're not going to be dealing with the tertiary amines in this chapter, but we will be dealing with primary and secondary amines. And for this video, we will just be dealing with the primary amines. So we'll hold off on secondary amines. We'll talk about those in a future video. All right, so we have these primary amines. Those are going to act as our nucleophile and attack the carbonyl carbon in this next reaction. So remember how last time we had in the formation of acetals, you take a ketone and you combine it with alcohols, the oxygen derivative of water, right? The carbon, taking water and replacing one of the hydrogens with carbon. Well, now we can take a ketone and replace it with the nitrogen version of an alcohol, an amine. What we're going to end up getting is a molecule. Now remember, this in the middle is an amine. What we're going to end up getting is a molecule called an imine. I-M-I-N-E, an imine. And that's sort of like the nitrogen version of a ketone. Or you could have, I guess, an aldehyde. So you have that double bond to oxygen to get the ketone. If you form a double bond to nitrogen, then you end up getting this imine. This is very common. This is a very common molecule in biological molecules. This is a very common feature of biological molecules, and these imines are also called Schiff bases. So if you ever see that term, that's just referring to the fact of an imine. It's the nitrogen version of a ketone. Now, whatever carbon chain was attached to the nitrogen to make it a primary amine, that carbon chain is going to be sticking off. Notice that oxygen, when it's stable, forms 2 bonds. Nitrogen, when it's stable, forms 3. So we're going to be forming these imines by adding primary amines. Just like in the case of acetals, there was a sort of halfway point where we had a hemiacetal. So likewise, in the halfway point in between ketones and amines is going to be a compound called a carbenolamine. And you'll see why that makes some sense when we draw it out. Now notice how the molecule is changing overall. You're taking 2 bonds to oxygen and you're replacing it with 2 bonds to a nitrogen. What would be in between that? Well, you'd remove one of the bonds to the oxygen, the other one would still be there, and you'd remove one of the bonds, and you'd add one of the bonds to the nitrogen, and the other one wouldn't be there yet. Now in this case, the oxygen is going to end up being a hydrogen, and we saw this. This should look very similar to what happened in the case of acetal formation. The ketone ends up turning into that alcohol before it leaves as water. And then this nitrogen, which started out with 2 hydrogens and a carbon, it's going to end up with carbon at the end, so it definitely still has that. It replaced one of the hydrogens with this bond to this carbon here, but it still has the other hydrogen there. And this neutral structure is a carbenolamine. Now again, this carbon can be any carbon chain. I should really put an R there. So that's a carbenolamine, and you can see why it's called a carbenolamine. You have an amine, nitrogen, with single bonds, that derivative of ammonia. You have an alcohol, so the suffix OL makes sense, and it's all bonded to a central carbon. Okay, so how can we get there? So now we're breaking this down. We sort of went from the satellite view and we're zooming in. So we know that this carbenolamine is sort of our check-in point, our halfway point. How can we get from the ketone to the carbenolamine and from the carbenolamine to the imine? What curved arrow patterns are we going to use? Well, in this case, for reasons we'll discuss in a second, you aren't able to protonate the alcohol, the ketone. In acetal formation, we did a proton transfer. We put a hydrogen on here to turn that into a better electrophile. We can't do that here, and the reason is because these amines are basic. So we are going to use acids in these reactions. You'll notice we still have these catalytic acids in brackets, like here toluene sulfonic acid. And when you put them into solution, a lot of them will turn into the waters. But another thing that the strong acids donate their hydrogens to is to the amines. After all, these amines are classic Bronsted-Lowry bases. When you first learned about Bronsted-Lowry bases, ammonia was the most famous one. It was the poster child for Bronsted-Lowry bases. That lone pair that just sits out facing the world, that could totally accept an H+. It could definitely accept a proton. And so these amines are bases. And if you add too much acid, then all of your amines accept all of the acids. Let's say we don't know what the acid is. It could be different every time, but it's always going to be giving an H away. In that case, when you do that, the amine ends up accepting the acid, the H+, and it ends up forming what's called an ammonium ion. So the ium there is referring to this charge. Now the ammonium ion, as you can imagine, is not a very good nucleophile. It has a positive charge on it. So if you make the solution too acidic, then all of your amines will turn into ammonium, and they won't be able to function as a nucleophile at all. Now that wasn't a concern in the acetal formation, but it is here. So the take-home message from that discussion is that you can't add too much acid. And because these ketones are actually pretty weak bases, you have to make the solution pretty acidic before they start accepting hydrogens. You can't add too much acid, and so you won't be able to speed the reaction up in that way, because you want to keep these amines as nucleophiles. So you can't make the solution too acidic. They'll all turn into really almost electrophilic ammonium ions. Okay, so we can't do the proton transfer at the very beginning. Instead, we're just going to hop right to it and do the nucleophilic attack. Our amine is going to attack the electrophile, which is the carbonyl carbon, electrophilic carbonyl carbon. So that's the first step. Now, after you get that step, both of these starting molecules are neutral. If they start accepting and donating electrons, they're both going to have charges. And so you're going to have to do 2 proton transfers to stabilize the charge on both of those molecules. 1 proton transfer to stabilize the charge that you're going to get on your ketone, the other proton transfer to stabilize the charge you're going to get in your amine. And once you do that, you should have the carbonyl amine. Now we are going to walk through all of these, so don't worry. We'll see these in detail. We're just sketching out an outline right now. Okay, so that gives us the carbonyl amine, and it should make sense that we have to do these. We're adding something, we're adding the amine, so we know we have to do nucleophilic attack. Then we have to balance the charges, so we have a couple proton transfers. Now if you compare the carbonyl amine and the imine, what are the differences? Well, we have to make this OH leave, so we know that we'll have loss of a leaving group. But it's not a good leaving group as it is right now. So we have to do a proton transfer to make it a better one. And that should sound familiar from the mechanism for acetal formation. After the leaving group leaves, we'll see that there will be a charge that we have to stabilize. And to do that, we're going to do another proton transfer. And so that is the full outline for the reaction that we're going to do. Nucleophilic attack followed by 2 proton transfers gets us from the ketone to the carbonyl amine. And then proton transfer, loss of a leaving group, another proton transfer gets us from the carbonyl amine to the imine. Okay, well, let's take this schematic and let's apply it in a couple examples with some concrete molecules. So the first thing to do is just to draw the specific ketone and the specific imine and the specific carbonyl amine that we're going to have here, and use those as our guideposts, so that as we're going through the mechanism, we'll get a sense of where we have to go and where we are. So our ketone has these 2 cyclohexyl groups. The imine we're adding is methylamine. So we have a nitrogen, 2 hydrogens, and a methyl group. That's this MeNH2. And the imine that we want, notice how the imine is related to the ketone. It's really the same exact thing, just the oxygen is replaced with a nitrogen. Double bond is still there. And whatever R group was on the amine, that's pointing off of the imine, the nitrogen and the imine. So there's our ketone and our imine. Now let's see if we can draw the carbonyl amine, the halfway point here. So we have 2 bonds to the oxygen. We're going to get rid of both of those and form 2 bonds to a nitrogen. At the halfway point, we're only going to remove one of the bonds to the oxygen, so that'll still be there. It'll be an OH. And we're only going to have formed one of the bonds to the nitrogen, so that'll be there. It'll still have 1 hydrogen and whatever R group it has here, that's a methyl group. So then we have the other cyclohexyl group, and that's our carbonyl amine. Okay. All right, well, now that we have this sort of outline, let's try to draw the mechanism. And before we do this, I'm going to lay out the steps on the side so that we don't ever get lost. We know this sort of flow chart, and we can follow it as we do the reaction. And I would encourage you in your mechanisms to also write out the steps even before you draw the mechanism, so that you always have a sense of where you are and where you're going. All right. In between, after that second proton transfer, we should have the carbanolamine. Just keep an eye out for that. And then at the very end, we just want to make sure that we have an imine. Okay, so these are our steps. So now we can take the ketone and we can react it with methylamine, the amine that we have. So that has 2 hydrogens and a methyl group. It's the lone pairs on that nitrogen, and the nitrogen is slightly negative because it's pretty electronegative. It's up there with oxygen, just to the left of oxygen, so oxygen's actually more electronegative, but yeah, the nitrogen is electronegative. It has that slight negative charge. The carbonyl carbon is slightly positive, right? The oxygen is slightly negative there, stealing the electron density from the carbon. So the nitrogen nucleophile comes in, attacks the carbonyl carbon, the pi bonds, the pi electrons break, and they go onto the most electronegative thing nearby, which is the oxygen. So now notice how that molecule changes. In some ways it's going to be very similar, but in some ways it will be very different. So what you want to pay special attention to are the charges. So notice that pi bond won't be there anymore. We're going to have an oxygen here. It's just one bond, and the oxygen will have 3 lone pairs on it. It had 2 to begin with. Now it has 3, so it has a full negative charge. And the nitrogen, which was neutral, still is bonded to 2 hydrogens and the methyl group. It's bonded to 4 things. That gives it a positive charge. So notice the charges here. We have 2 of them, a negative charge and a positive charge. To stabilize those, we have to do proton transfers. And since we have 2 positive charges, we're going to do 2 proton transfers. Now you do have to add some acid to this reaction. You'll see that the acid is really a catalyst. You just can't add too much. The preferred pH for this is around 4.5. Now if it's too high, then the reaction won't work, and if it's too low, the reaction also won't work. You will want it to be around 4.5. That gives you an equilibrium where you have amines that can act as nucleophiles, but you also have these hydronium ions that can do their catalysis. All right, we have our hydronium. That hydronium can donate an H to the oxygen. This oxygen can pick off one of those slightly positive hydrogens. The electrons can go onto the oxygen to stabilize the positive charge there. So that's a proton transfer. The molecule we have will be almost the same as this, except now, instead of a negative charge, we won't have that, and the third lone pair will turn into a bond to that hydrogen. So we transferred a proton. We transferred this hydrogen from one molecule to another. Okay, well, we stabilized the negative charge. Now we just have to stabilize the positive charge. We can take the conjugate base that we just made. So here we made water, right? When this lost that hydrogen, it became water. And that water can act as a base and steal one of the slightly positive hydrogens on this ammonium ion. The electrons snap back onto the nitrogen, and so we get a molecule that's very similar. But that hydrogen isn't there anymore. The electrons went to stabilize the positive charge. And you can see that we do, in fact, have our carbanolamine where we expected it. We have a carbon that's bonded to an amine and an alcohol. And so that's the carbanolamine. Okay, well, we're halfway there. We took off one of the bonds to the oxygens and we formed one of the bonds to the nitrogen. Now we just have to do that again. We want to remove the OH altogether, but right now it's a bad leaving group. So to make it a better leaving group, we can do a proton transfer. We can take some acid. We can take the acid we formed in that last step, and that hydronium can donate one of its H pluses to the carbanolamine. The slightly negative oxygen here can steal one of those hydrogens. The electrons snap back onto the hydronium oxygen to stabilize the positive charge, and that is a proton transfer. So what that gives us is it turns our molecule, it turns our poor leaving group into an awesome leaving group. The OH was a bad leaving group. Now that it has an H and a plus, it's an awesome leaving group. All it needs is a small push, and the molecule will come off. Well, we have a similar case here as with the acetal formation. This carbon in the middle of the carbonylamine is really slightly positive because it's bonded both to a nitrogen and to an oxygen. Both of those are stealing its electron density. So it's really slightly positive. And so the nitrogen, which is slightly negative, has been eyeballing it this whole time, trying to form a second bond to it. But the other thing bonded pushes it back. Well, now that the other thing is a good leaving group, when it tries to form a pi bond toward the positive charge, that kicks the leaving group off. And we get loss of a leaving group. And the molecule that we have left we now have a double bond to the nitrogen. The nitrogen has a methyl group on it and a hydrogen. That's 4 bonds. That means it's an ammonium ion. And water is off to the side for now. But it popped off of the molecule there. Okay. Well, we're almost at our imine. We just have to stabilize this positive charge. And we can do that by treating this water as a base. The slightly negative oxygen can come in, swoop in, and like 2 little talons, the electrons in the lone pair can steal a slightly positive hydrogen. The electrons ricochet back onto the nitrogen, which needs them to stabilize its positive charge. That's our proton transfer. And what we end up with is our imine, the nitrogen equivalent of a ketone, our Schiff base, very common feature in biological molecules. So what we did was, overall, we did nucleophilic attack with the amine. The amine attacks the carbonyl carbon, nucleophilic attack. And then to stabilize the charges that are created, we did 1 proton transfer, followed by another proton transfer. Then we needed to kick the oxygen off altogether, so we had to make it a good leaving group, so we did yet another proton transfer, and at this point we had the carbonylamine. Once we turn that into a good leaving group, it gets kicked off the molecule through loss of a leaving group, and to stabilize the imine that formed, we did just 1 more proton transfer. Okay, let's see that reaction in one more context. So let's take this schematic that we've built up, and we're going to think about that in the context of another formation of an imine. So similar reaction. We're going to erase the specific molecules, but you'll see that the process is really the same. We're still taking a ketone, reacting it with an amine, and getting an imine. In the middle, we get a carbonylamine, and it happens through the same sequence of steps. In addition to that, let's take those steps and write them out separately so that as we go through the reaction, we can track our progress. We can get a sense of where we are and where we're going. And I encourage you to do that when you write out your mechanisms. To write out the steps in the order that they should happen in first. Write in the big landmarks. So for example, after the second proton transfer, and this should really have that P there, after that second proton transfer in the reaction, you should have the carbonylamine. Then you do those next 3 steps, and at the very end you should have your imine. Okay, Well, let's fill all this in. The ketone we have is cyclobutanone. The imine we have is ethylamine. So that's a nitrogen with an ethyl group on it and 2 hydrogens. Don't forget the lone pair at the top of the nitrogen. And then we have an imine. That turns into the nitrogen version of itself. Double bond to a nitrogen, and the R group, which here is an ethyl group, stays there. Notice that's CH2, CH3. That's what the ET is standing for. Now the carbonylamine is going to have the same carbon backbone, but we're going to have 1 bond to the oxygen instead of 2, and that will be stabilized by a hydrogen, so it'll be an OH, and we'll have formed only 1 bond to the nitrogen. So it'll still have its ethyl group, and it'll still have 1 more hydrogen. So we have an amine and an alcohol bonded to the same carbon. That's a carbonylamine. Okay, let's go through the steps for this, starting with cyclobutanone and ethylamine. Well, we can't speed this up by making by doing a proton transfer to make the carbonyl even more electrophilic, because the amine is basic. It would steal all the hydrogens. It's more basic than the ketone is, so it would steal all the hydrogens itself, become ammonium ions, and then it can't function as a nucleophile. So we only will add a little acid so that this exists in equilibrium with the ammonium version of itself. Exists in equilibrium. And that means that we'll still have this to act as a nucleophile, and later we'll still be able to use an acid. But in this first step, we must rely on the power of the nitrogen to attack the carbonyl carbon. Carbonyl carbon is slightly positive because its electron density is getting stolen by the oxygen, which is slightly negative. The nitrogen is slightly negative, and it's got that lone pair, so it swoops in, attacks the carbonyl carbon, the pi bond breaks, goes to the more electronegative atom. The electrons go onto that oxygen there, which had 2 lone pairs. After that nucleophilic attack, that is going to have 3. Oops. So the oxygen gets, one of the bonds gets broken. It has 3 lone pairs on it now, full negative charge. The nitrogen now has a bond there, but it's bonded to 2 hydrogens and an ethyl group. That means it has 4 bonds and is an ammonium ion. Now there are 2 charges there. We have to stabilize both of them, and we're going to do that by doing 2 proton transfers. In the first case, we're going to add our acid. Now they gave us some fancy acid, toluene sulfonic acid. We have talked about that in a previous mechanism. But the point is that that's a strong acid. When you put that into a watery solution, it's going to give all of its H's away and turn into hydronium, and then a stable conjugate base of the toluene sulfonic acid. So the acid we're going to use here is hydronium. That's the acid that ends up sticking around in solution with the H pluses. And so the negative oxygen steals one of the hydrogens from hydronium. The electrons snap back onto the oxygen to stabilize the positive charge there. So after that proton transfer, we end up with a molecule that's pretty similar. But instead of that negative charge, now it has a single bond to a hydrogen. So no charge there. And the hydronium ion turned into water. Well, the water can swoop back around and help us out to stabilize that other positive charge on the ammonium ion. Here, the slightly negative oxygen can steal the slightly positive hydrogen, and the electrons that were keeping the hydrogen there will snap back onto the nitrogen to help stabilize its positive charge. Well, that whole thing is a proton transfer. We're transferring a hydrogen from one molecule to another. And the product we get when we do that is very similar, but it doesn't have this hydrogen here, and it doesn't have the positive charge. What we have at this point is the carbonylamine. And you know that it's the carbonylamine because you have a carbon that's bonded to an amine and an alcohol on itself. Like just one carbon has both of those features bonded to it. That makes that a carbonylamine. So we're halfway there. We're halfway to the imine, or the Schiff base. All we have to do is get rid of this OH and make another bond to the amine. To do that, we have to make this a leaving group, but it's a bad leaving group right now. So we have to do a proton transfer to turn it in to a better leaving group. Now we can use the hydronium that we made in the previous step. We made H3O plus in this previous step. That can act as an acid. The slightly negative oxygen steals one of those hydrogens. The electrons snap back onto that hydronium oxygen. And now the carbenolamine gets protonated. Instead of a lone pair, we'll have a bond to a hydrogen, full positive charge. So we did that proton transfer. We did the proton transfer to turn this into an awesome leaving group. We want to kick the oxygen off of the molecule. Well, now, it doesn't take much, just a small push. The carbon in between the oxygen and the nitrogen is very slightly positive. Its electron density is being stolen by both of those atoms. So the nitrogen, which is slightly negative, has been eyeballing it this whole time. These electrons have been trying to form a pi bond there. Usually it gets rebuffed and pushed back, but now, when it goes to try to form a pi bond there, it kicks off the water molecule. And we end up getting loss of a leaving group. Water is off, living its best life. And now we have a pi bond to the nitrogen. The nitrogen has an ethyl group on it and a hydrogen. That's 4 bonds on that nitrogen. That gives it a positive charge, makes it an ammonium ion. Well, we almost have our imine, or our Schiff base. All we have to do is stabilize that positive charge by doing, yeah, you guessed it, stabilizing a charge. You know what to do, proton transfer. So that's what we're doing here. The base is going to be the water. The water, the slightly negative oxygen swoops in, steals the slightly positive hydrogen. The electrons snap back onto the nitrogen to help stabilize the positive charge there. And after that proton transfer, you end up with your imine, your Schiff base, the nitrogen version of a ketone. So in that whole mechanism, just like in the mechanisms we saw before, it's very similar to what happened in the case of forming acetals. But the first step is the attack of the nucleophile on the carbonyl carbon. Once you have that, we had to stabilize the charges that formed with 2 proton transfers. So stabilize one charge with a proton transfer, stabilize the other charge with a proton transfer. That gave us our carbenolamine. Then we wanted to kick the oxygen off, so we did a proton transfer to turn that into a good leaving group. It gets kicked off by the nitrogen, so loss of a leaving group, and we stabilize the positive charge that forms with a proton transfer. And that gives us our beautiful imine. So this reaction happens very, very often in biological systems. You'll see it in biochemistry, and hopefully now it won't just look like a mystery, black magic transformation, but something that makes sense. It's something that